So the next, what we need to cover until the end of the lectures today is eigenvalues, eigenvectors, and orthogonal matrices. And if we have time, we might start talking about symmetric matrices. But the symmetric matrices do not appear in this assignment, it appears in the next assignment. So, after understanding what a matrix is, we need to understand what is an eigenvalue and what's an eigenvector of a matrix. So, we have said that a matrix takes vectors or takes a circle of vectors or a ball of vectors, depending on what dimension I'm talking about, and gives me some sort of an ellipse of vectors. In this procedure, some vectors change their length and their directions. Usually vectors change both their length and their direction. If a vector does not change its direction, then it's called an eigenvector. So if a vector, after this transformation, keeps its direction, but gets longer or shorter, then it becomes an eigenvector. So the definition is as follows. If M is an n by n matrix, lambda is called an eigenvalue of M if there is a vector. This vector is not the zero vector. Such that when I take the image of x, which is mx, it's actually a multiplier of the original vector x. And so x keeps its direction. This is x, and this is a multiplier multiplied by x. It could be negative, but it's still in the same direction. Lambda could be negative, but it's still in the same direction. In fact, lambda could also be equal to 0. If lambda is 0, it's also, because I did not put any restriction on lambda, I just made sure that the x is not equal to 0. So, this is the definition of an eigenvector. X is called an eigenvector. Now, how you find an eigenvector is a different story. To find an eigenvector, what you usually say is, I know that mx is equal to lambda multiplied by x, which means that m minus lambda I multiplied by x is equal to the 0 vector. X is not 0, that means that m minus lambda I cannot be inverted. M minus lambda I cannot be inverted, then I say, okay, well, let's find the determinant of this matrix, because it's a measure of whether this matrix is invertible or not. And so I take the determinant of m minus lambda I, and I say this is equal to 0 to make m minus lambda I not inverted. And then I can find this, once I find this lambda, now because we're working in R3, in M3, the equation, the determinant is a cubic function of lambda. Because it's a cubic function of lambda, we expect either one real solution and two complex solutions or values for the solution for lambda, or three real solutions. So the first question, or the first problem, is we need to find the eigenvectors and eigenvalues of the identity matrix I. Now before you jump into, okay, let's calculate I, the determinant of M, or before you jump and say, okay, determinant of I minus lambda I equals 0, and jump into the procedure of calculating the eigenvectors and the eigenvalues, you should right away, from the definition, predict what the eigenvectors and the eigenvalues are. Because what happens when I multiply I by any vector x? I get x, which means x does not change its direction and does not even change its length. Which means right away any vector is an eigenvector of I. And all these vectors are associated with lambda equal 1, because this is equal to 1 multiplied by x. So from the definition, right away, for every x in R3, x is an eigenvector associated with lambda equal 1. So all of the vectors in R3 are actually eigenvectors of I. If you do it that way, you're gonna get this same result. Find the eigenvectors and eigenvalues of the matrix M. Now, basically, I would like to make this matrix 1 minus lambda 0, 0. I want it to be not invertible. Right away, I know that if I make this 0 and this 0 and this 0, this matrix will not be invertible. And you'll find from the function, from the formula for the determinant, to make M minus lambda I not invertible, lambda is equal to 1, lambda is equal to 2, lambda is equal to 3, and for lambda equal to 1, I'm looking for the corresponding eigenvector. What's x that will give me the 0 vector? Which means 0, 0, 0, 0, 1, 0, 0, 0, 2, multiplied by x1, x2, x3, equal to the 0 vector. What should I put here to give me the 0 vector? You'll find that I can put x1 is equal to 1, x2 is equal to 0, x3 is equal to 0, therefore x is equal to 1, 0, 0 is eigenvector associated with lambda equal 1, which means if I take m multiplied by x, I'm going to get 1 multiplied by x. And notice the following. If if I have an eigenvector, any multiplier of that eigenvector is still an eigenvector. Because if I put here x is equal, or y is equal to, let me write this. If x is an eigenvector of M, then any multiplier by x, where alpha is a real number, is also an eigenvector of M. Because of the linearity of the matrix, M multiplied by x is equal to lambda multiplied by x. M multiplied by alpha x, any real number, because of the linearity, this is equal to alpha mx. As long as alpha is not equal to 0, this is equal to lambda alpha of lambda x, which is equal to lambda multiplied by alpha x, which shows that alpha x is also an eigenvector for it. So any of those, any multiplier by this vector will be an eigenvector. So I'm going to now to show you how to find or how to manipulate matrices in mathematics. Now there are many tutorials on online, so you should follow those tutorials as well. But it's just going to be a repetition of what we're going to say here. So, I haven't shown you anything in mathematics, right? No. So to define a vector, in general, you write x, and you open a curly bracket, which is basically what we're using in the course, curly brackets, and put whatever values we want. Let's put a vector. The nice thing about Mathematica is that I can put a vector ABC. Mathematica is case sensitive. You guys are going to be reading my email here. It's case sensitive, so if I define another variable that's capital X, that's a matrix. I'm going to define a matrix with a capital letter. X is different from small x. To define a matrix, it's a list of vectors. So it's a big list. Inside that list, I have 3 other lists. That's called the first vector, A, also B and C, and the other one C, D, and E, and then E, F, and G. The nice thing is, in any other software that you know, if you multiply X, and you say, I want to multiply this matrix by this vector, you're going to get an error because you have not really given any numbers to those values. But in Mathematica, you haven't given any numbers, but if you say, I would like to find the vector when I multiply X by X, shift enter, and you get the result. This is the vector that comes out of the multiplying A, B, this matrix by this vector. And you can call this Y, and if you put semicolon, you will suppress the output, and notice that I'm writing everything in the same cell. So I'm not evaluating anything. When I press enter, I'm not evaluating anything. Only when I press shift enter, then I start evaluating everything in that particular cell. Shift enter will give me y in a matrix form. Semicolon, the semicolon suppresses the output. The only output I see is y in matrix form. To take the dot product between vectors, let's take x dot y, and this is the value of x dot y. And notice that when I multiply matrices for vectors, I'm using the dot, not the star. If you want to cross, I can take the cross product between x and y, and then I can show it in matrix form. This is the result of taking the cross product between x and y, and I have not really given any numbers for ABC or any of those numbers. At any time, you can give me values for ABC and then evaluate this function again. So you can say A is equal to 1, B is equal to 1, and C is equal to 5. And just evaluate here. Let's first put Z is equal to this, shift enter, and then after in that new cell, find Z, find Z, shift enter. Now Z will have a value after putting A, B, and C with these values. Now, A, B, and C have these values. I'm going to start from scratch, evaluation, and quit because I don't want any variables stored in Mathematica. I'm going to remove this cell. Like there is a trick for which I can evaluate the function or at a certain particular numbers for the variables without really assigning numbers to those values. So I can evaluate. So Z right now is equal to this. I can ask Z to be evaluated and open a curly brackets when A, I'm not saying equal, I'm saying tends to 1, B tends to 1, C tends to 5. In matrix form. Now, I have not really assigned the value for A or B or C, only for this last evaluation. If you actually print Z again, shift enter, Z has not changed. I just said evaluate Z when A is equal to 1, B is equal to 1, C equal to 5. I can even say that D is equal to Z when you assign those values to it. Okay, I've done something. Oh, yes. I already used D here, so there's a big. So you can see here, I defined Z as the cross product between X and Y. I evaluated Z at these values, and then I have a new vector called D. D, this vector is equal to Z when A is 1 and B is 1 and C is 5. D is equal, so you can see that D already has A, B, and C evaluated. Z still has A, B, and C unevaluated, and you have not really lost the formula using this trick. These are called rules. Mathematica calls them rules. And somebody asked me earlier to have a note. All you have to do is just put a bracket, star, and put whatever note you want. And you can also say print if you want the output to be, if you want something to be printed to the output, you can in fact print. You can, if you want to make things look pretty, print dd, comma, dd in matrix form. I think that's how you do it. Shift enter. And you say here dd is equal to this. So you separate your entities by commas, and you get everything that you want. Print. So I have a matrix X and I have a vector small x. Sometimes I'd like to get, for example, I have a vector called dd. Let's say I would like to take the third element in dd. To extract the elements or the entries inside vectors and matrices, you use square brackets. Two sets of square brackets. dd of 3 gives me the third element in dd. The third row and the first column in dd will give me, shouldn't give me anything. Well, it shows negative 22. But in general, I didn't know you could do that. In general, if you want an entry inside a matrix, the matrix X, the third entry is a vector. Let's just put X here so that you see it. And the third entry, the second, is an element. So X in matrix 4 is this. The third entry in X is the vector EFG. And the second entry in the third vector is the element F. So to extract elements of matrices or vectors, you use the square brackets. To calculate the eigenvalues and the eigenvectors of a matrix, or before the eigenvalues or the eigenvectors, to transpose a matrix, all you have to say is, let's say xt is equal to the transpose of x. And that's view xt in matrix form. This is the transpose of x. To find the determinant, you just type the determinant of xt. And this is the determinant of the matrix. Again, function of all those variables, you don't have to evaluate any of those variables for now. In fact, I hope it works. I can invert this matrix. Let's call it xt negative. Sometimes you get those huge formulas. You can use a function called full simplify, xt negative, and view the result in matrix form. Didn't really do much. You can define a matrix, which we will see later, we'll need in the other chapters. You can define matrices using tables. So let's say, or vectors using tables. Let's say I want to define a vector that's equal to 1, 2, 3, 4, 5, 6, 7, 8. So when I is 1 to 8, and here's my vector. Or it could be 2i, whatever formula I want. the same way, I can define a matrix as a table. Let's say I multiplied by j. I is 1 to 3 and j is 1 to 5. And let's view the matrix in matrix form. Now shift enter, and here's your matrix. The last function that I want to talk about is how to calculate the eigensystem or the eigenvalues and the eigenvectors of a matrix. So I'm going to define a matrix. To calculate the eigenvalues and the eigenvectors, you type eigensystem of the matrix, shift enter, and you get this list. Let's view this list in an easier way. So I'm going to save this list in a variable called A. And I'm going to view A in matrix form. In matrix form, this huge list is made out of the following. The first row is made out of the eigenvalues. And the second row is made out of the eigenvectors. The first eigenvalue corresponds to this eigenvector, and the second eigenvalue corresponds to this eigenvector. So if I want the eigenvalues, the first eigenvalue is the list A. So eigenvalue 1 is equal to this list A. I need the first row, the first entry. Eigenvalue 2 is the first row, the second entry. Eigenvalue 3 is the second row, the first entry. Eigenvector 1. Eigenvector 2 is the second row, the second entry. Shift enter. This is the first eigenvector, the second eigenvector, the associated eigenvalue. Eigenvalue 1, eigenvalue 2, eigenvector 1, eigenvector 2. And you can see that the vector is between a curly bracket. Alright, do you guys have any questions about how to do this here? Alright, so let's now go back and discuss another important topic, which is orthogonal matrices. So for 664, there are three types of matrices that we want to study. The first is called a rotation matrix. So we need to study rotation matrices, symmetric matrices, and skew symmetric matrices. Each of those has a specific function that's very important for geometry and for deformation. A rotation matrix describes rotations and tells me that objects are rotating in space. A symmetric matrix tells me that an object is not rotating in space, it's just stretching. And a skew symmetric matrix tells me that a matrix or an object is just about to rotate, and it's rotating in space with a certain speed. So all these matrices are important for the study of continuum and solid mechanics. And the first one that we need to study is a rotation matrix. A rotation matrix does the following. I have an object in space, an object in space is described by the vectors of the points in it. So it's described by these vectors. Rotation matrix Q takes those vectors and rotate them by a certain angle to give me this new rotated object. There is another reflection matrices as well, which they fall under the same category with rotation matrices, which when you take an object here, you can just get a mirror image of that object. So, but you get the same distances and everything, but just a mirrored shape of the mirrored object, or the mirror of that object. So what we're going to study now is these kinds of matrices, which either rotates or reflects, and these matrices are called orthogonal matrices. So what are orthogonal matrices? Orthogonal matrices are defined as follows. Q is an orthogonal matrix if the associated n vectors are orthogonal. Let's look at it for if Q is a 3 by 3 matrix. What does it mean? It means that Q, which is equal to A1, A2, A3, B1, B2, B3, C1, C2, C3, A, B, and C are each, the size has 1, and the 3 are perpendicular to each other. What does it mean that they're perpendicular to each other? It means the following. If I take Q and I take its transpose, this is A, this is B, and this is C. The first entry here is equal to A dot A. It's the dot product between A and A. The second entry here is A dot B. Third entry is A dot C. B dot A, B dot B, B dot C, C dot A, C dot B, C dot C. Now these vectors are orthonormal. It means what A dot A is equal to the size of A, which is equal to 1. A is perpendicular to B, so A dot B is 0. A dot C is 0, and so on. So you get the identity matrix. But we define the inverse of a matrix, that when you multiply the matrix by its inverse, you get the identity matrix. Which means that for these types of matrices, the transpose is actually the inverse. Now there are a few results for this that are important. So the determinant of Q is equal to the determinant of Q transpose, which is equal to the determinant of Q minus 1. Which is also equal to 1 over the determinant of Q. Because we said the determinant of Q minus 1 is equal to the 1 over the determinant of Q. Which means that all this is equal to either positive 1 or negative 1? If Q is a 3 by 3 matrix or a 2 by 2 matrix, if the determinant of Q is 1, it's a rotation. If the determinant of Q is negative 1, it's a reflection. Basically, if the determinant of Q is 1, that means that if I have a V, U, and W, and I take Q and apply it to those three vectors, I'm going to get QV, QU, QW that have the same orientation to each other. That's what a rotation does. If Q is a reflection, I have V, U, and W, I will get QV, QU, and QW on the other side. In component form, Q transpose, this matrix is equal to the matrix I. In component form, Q transpose is a matrix has ij is equal to the component form of ij. Now we said the component form of this is delta ij, the Kronecker delta, which when I is equal to j gives me 1, when I is not equal to j gives me 0. Q transpose ij is equal to qi, qj, and k, but the second one is transpose, so I'm going to transpose those. And there is a summation over k that's implied. So the free component delta ij, or the component entry delta ij, is equal to qik, qjk, and the summation is done over k. And also, Q transpose Q is equal to I, which also means QKI, QKJ is equal to delta ij. Again, summation over. If I apply a rotation, Q1, and then I apply another rotation, Q2, then, so this is rotation, in Q1, Q2, which is the matrix that corresponds to the two operations together, Q2. Notice I apply Q1 first to the vector, and then I apply Q2 to the vector, so it's Q2 dot Q1. This is also a rotation. The function of the rotation matrix is to rotate vectors, but there are two functions of the rotation matrices, and you have to be very careful the difference between those two functions. To rotate vectors, so for example, if this is u, the function of q is to rotate u into the new vector v, and if that rotation is in this direction, then the form of q is given by those vectors a and b that's rotated in the opposite direction. So Q in this form will be equal to cosine theta, negative sine theta, cosine theta. When we talk about the orthogonal change of basis, it will be different. So other examples. I is a rotation matrix. It's a rotation matrix with an angle of 0 degrees. Because I is an orthogonal matrix, the three vectors are orthonormal, and the determinant of y is 1. This is a reflection matrix. What does it do? It takes a vector and takes its x components and gives you the negative of its x component. So if you have any object, it gives you the mirror around the mirror image of that object through the plane E2 and E3. The order of reflection is very important, or the order of rotation is important. And you will find an example in your text. If you copy and paste the code into Mathematica, you will see how the order of rotation is important. Qx, Qy, Qz is not equal to Qz, Qy, So there are a few examples. You can copy and paste the code. And for example, this code shows you that when you rotate an object around x and then rotate it around y and then rotate it around z with a certain angle, you don't get the same result if you use the same angles but in a different order. The second function of rotation matrices is the change of basis. Now this is a very important topic for the following reasons. You're doing an analysis, and this analysis produces certain results. So you're analyzing this object, you're finding the stresses and the strains inside this object, and you assume that this is your x-axis and this is your y-axis. Another person assumes that this is their x-axis and this is their y-axis, but it's the same object. I need to be able to translate between the numbers that the person gets in this coordinate system and the number that the other person gets in the other coordinate system. I need a translation between the numbers. Because a vector here will have certain values, a vector here will have different values. For example, if this is 1, 1, this vector might be 5, negative 1, for example. So they're not the same numbers. And when you calculate the stresses and you calculate the strains and all, you're going to get totally different numbers. How can you translate between the two? You translate the two using an orthogonal matrix. And usually this is a rotation matrix because we keep the order, we always follow the right-hand order. So this is always a rotation matrix. Now Q, this rotation matrix, is made out of the following. This is x and this is y. I bring x prime and put it here. I'm going to call now this E1 and E2. I bring E prime and put it here. E2 prime and put it here. And Q is made out of the following elements. The component of E prime in the direction of E1, the component of E prime in the direction of E2, the component of E prime 1 in the direction of E3, which is basically E dash 1. The components of E dash 1, this is the vector. This is the component of E dash 2 in E1, E dash 2 in E2, E dash 3 in E3. So you get this matrix that's made out of those vectors. And so if, for example, in R2, this is E1 and this is E2 and this is the vector U, if same vector U, and now I'm using E dash 1 and E dash 2 with an angle theta, then Q will be equal to cosine theta, sine theta, negative sine theta, cosine theta. It's not the same matrix that we produced in the previous example, when we discussed rotation. When we discussed rotation, you had a different matrix. It was the transpose of this matrix. Okay? Because that's a lot of students make that mistake. When I'm changing the coordinates, all I have to do is just find those E dash 1 and E dash 2, the new coordinate system, and put the new coordinate system in that matrix with each of those vectors as rows. When I'm rotating, it's a different story. When I'm rotating vectors, it's a different story. Here, the vector keeps its direction. So, how do you now translate between the two vectors, or between the two vector spaces? They're the same vector spaces, but a different language. This one is using E1 and E2 to describe everything. This one is using E dash 1 and E dash 2 to describe everything. It's going to be very easy to show, and you should read the proof of this, that a vector U here, its components are equal to U1 and U2 in this coordinate system. The new vector in the new, it's the same vector but written in the new coordinate system, is equal to the entries of Q multiplied by U1, U2. And it's very easy to write this, knowing the relationship between E dash 1, E dash 2, and E1 and E2. So, a vector, if you use B is equal to E1, E2, and En, then U prime, a new vector, using a new coordinate system, E dash 1, E dash 2, E dash 3, and so forth, E dash N, U prime is equal to Q multiplied by U, where Q is equal to E dash 1 dot E1, E dash 1 dot E2, and so on. U prime I is equal to Q ij uj, where summation is implied. So this is how a vector translates. This is how I translate between the vectors in the different coordinate systems. Now what about matrices? To understand how a matrix translates between the two coordinate systems, I'm going to do the following. If this is vector u, if I have a matrix that takes the vector u and gives me another vector m u, let's call it v. Q gives me the u, it translates between the two languages. This is u prime is equal to qu. V prime is equal to qv. It's also equal to m prime u prime. I would like to know how m prime relates to m. I know that u prime relates to u using qu. How does m prime relate to m? I'm going to just use the relationship between v and qv. I know that v prime is equal to qv. And v is equal to mu. Also, v prime is equal to m prime u prime. And u prime is equal to qu. So, I'm going to look at this and this. Qm, the matrix Qm by u is equal to the matrix m prime qu. U is arbitrary, which means the action of this matrix is equal to the action of this matrix, which means that this matrix is equal to this matrix. Q is an orthogonal matrix, so then U m prime is equal to Q m Q transpose. So vectors translate using this formula, and matrices translate using this new formula. There is an example here to show how to do this. You have a vector x, a vector u, and a vector v, and a vector w, and we have a linear map represented by the matrix M. So I have x here, and I have u, v, and w. And I chose u, v, and w. If you pay close attention, u, v, and w are orthogonal. So I have a vector x that's equal to 1, 1, 1. The first question is find the component vector y, the image of the vector x under the linear map M. Y is equal to mx. If you take m and multiply by x, you're going to get the y. Show that the vectors u, v, and w form an orthonormal basis set. You're going to find u dot v is equal to v dot w is equal to u dot w is 0, and the length of each is 1. Therefore, there are three linearly independent vectors, and they are orthonormal. Therefore, they form an orthonormal basis set. So I can use e-1, e-2, e-3 as u, v, and w. And now I have a new basis set made out of those three. To translate between the components that I have here and the new components, I need a translation matrix. This translation matrix will be equal to the new component, to the components of e-1, e-2, e-3. This Q is made out of u, 0.6, 0.80, v, which is negative 0.8, 0.60, and w, which is 0, 0, 1. So So now we need to find x, y, and m in the new coordinate system. What's x if I chose e-1, e-2, and e-3, and what's y and what's m? The new x prime will be equal to this q multiplied by x. The new y prime will be equal to q multiplied by y. The new m prime will be equal to q multiplied by m by q transpose. The last topic that we want to discuss today is vector and matrix invariant. So we agreed that if I have an object here, I'm analyzing in this vector space, another person might choose a different coordinate system where they talk to each other using a matrix called Q. I'm interested because all my design usually is based on numbers that I get from my analysis. We want to make sure that the person who analyzes this object in this coordinate system makes the same decisions as the person who analyzes this object in that new coordinate system. Which means whatever numbers you use here should be the same numbers for design that you use in the new coordinate system. You can't tell me that in this coordinate system the maximum stress was 100, but in this other coordinate system the stress is 50. So basically you can reduce the size of your component because the stress in the other coordinate system is less. Whatever design numbers you need for the design here have to be the same as here. And those numbers are called invariants because they do not vary with the change of coordinate system. So there are vector and matrix invariants that do not change when I change my coordinate system. The first is, of course, I expect the length and angles not to change. I know that the size of u is equal to u dot u. In the new coordinate system, qu, or the size of u prime, is equal to qu dot qu. I'm going to use the abstract definition of transpose to take the transpose and put it here. Q transpose Q is equal to I. It's the identity matrix because the inverse of Q is equal to its transpose. So this is equal to U dot IU, which is equal to U dot U, which gives me the length of U squared. So lengths do not change. And similarly, QU or U prime dot V prime, where of course U and V are in R3 and Q is orthogonal. The angle between U and V after rotation is equal to QU dot QV. Again, I'm going to use the abstract definition of the transpose because it makes manipulation of the formulas much easier. U dot Q transpose QV, this is I get U dot V, which means before and after, or after and before, I get the same dot product, which means the same angle. Usually, the design is based on the stress, and the stress is a matrix. Usually, the design is based on what we call stress invariance. The one means stress, if you've ever heard of it, the hydrostatic stress, and all these stress measures. These stress measures are invariants under the change of coordinate system. So we need to measure measures of the matrices that do not change when I change the coordinate system. If I have the matrix that is a 3 by 3, there are 3 invariants for n. first invariant is called I1 of m, or is equal to trace of m, is equal to the sum from I equal 1 to 3 mii, or mii for short, and the summation is m1, which is basically m11 plus m22 plus m33. The sum of the diagonal components is equal. Whatever coordinate system you use, the sum of the diagonal components is equal. Let's check it out. I1 of m prime. This is equal to I1 of q m q transpose. This huge matrix is made out of the multiplication of three matrices. So this is q m q transpose I, a huge matrix. I took the component for the summation I summed over I, which basically is equal to the following: q m q transpose. Put I here, and I should put I on the outside, but because it's transposed, I'm going to put I inside, and then in the middle I'm going to sum k l l. And there are summation signs everywhere. There's summation over I, there's summation over k, and there's summation over l, because this is just a number, and that's why there's not a free index. qik, qil, mkl, and there's all sorts of summation here. I'm summing over I, k, l. But I know when I sum over I, qik, qil, this will give me, if you look at the component form of the q's, this will give you delta kl. Here I'm summing over k and I'm summing over l. So this is summing over k from 1 to 3 and l from 1 to 3. But this will only give me 1, or will only give me a value when k is equal to l. So this is equivalent to summing over k. Summing over k is the same as summing over I. It's just a dummy. This is equal to mi, which means that I m prime, I1 of m prime, is equal to I1 of m. Which means the diagonal components, the sum of the diagonal component in any coordinate system stay the same. The second invariant, or let's talk about the third invariant, because it's easier. It's actually the determinant of m. Because the determinant of m prime is equal to the determinant of q m q transpose, and we said the determinant of q multiplied by the determinant of q transpose is equal to 1. So these two are equal. So the determinant of m does not depend on which coordinate system you're using to express m. The third invariant, or the second invariant, is equal to half I1, first invariant of m squared, which is already invariant, minus I1 of the matrix that's equal to m multiplied by m. And since this is invariant and this is invariant, this will be invariant as well. Now, these appear so these three expressions which are I1 of m, which is equal to m11 plus m22 plus m33, and I2 of m, which is a function of the components of m, and I3 of m, which is a function of the components of m, these three expressions appear in the eigenvalue problem for m. When you take the determinant of m minus lambda I, you get those expressions. And since these expressions do not depend on the coordinate system, what does this mean? That's the last thing. If I get the same equation independent of the coordinate system, it means that the solution to this equation will not depend on the coordinate system, which means that the eigenvalue is not dependent on the coordinate system. Whatever coordinate system I use, I will get the same eigenvalue for m. Same eigenvalues. Same eigenvectors as well, but they have the same direction, but will have different components. We describe the matrix invariance using the components forms. There are, if you've studied continuum mechanics or planning on studying the continuum mechanics, you should read this section because you can define the I1 of m and I2 of m and I3 of m without using components, but with using three linearly independent vectors. And you can define them as, you have certain expressions, so check those expressions. I will write you I3 of m. I3 of m, which is equal to the determinant of m, for example, is equal to ma dot mb cross mc divided by a dot b cross c. And those who work in continuum mechanics who don't like to use components prefer the alternative forms of matrix invariance. Alright, so the assignment 2 is due next week, and next week we're going to cover symmetric matrices and skew symmetric matrices, and we'll cover some other, we'll finish this and start stress, the mechanics part of the course, and the week after the lecture is cancelled. But next week there is an